Good morning, everyone. It's a pleasure to have Boris Altshuler here with us today. So Professor Boris is visiting us for a month, and I will briefly introduce him to you. So he completed his studies in St. Petersburg University, and he's now a professor in Columbia University. And he works with theoretical condensed matter physics. It's an honor to have him here for a month, and in particular today giving a talk. So he'll be talking about the possibility of reaching room temperature superconductivity. So please, Boris, take it away.
No. Yeah. It maybe we better turn it off because it looks like there is some echo around. Oh, it's okay. Yeah. Mm-hmm. Okay, so first of all, I want to thank Alvaro and all of you for inviting me here. I'm having a great time and hope to learn more about what people here are doing and get some new ideas. So I'm here all the time for another 2.5 weeks. So if you would like have some questions about what I will speak today or any other questions, please don't hesitate to come to my office. So what I am going to discuss today is a story which has both experimental and theoretical components, because I need to have a good idea what is main interest of people here. So it would be kind of talk for general physics, but there would be some theoretical challenges and ideas as well. And to start with, I want to acknowledge collaboration with Emil Yusbashan, who is a professor at Rutgers, and our experimental colleague Dmitry Semenyuk, and Aniket Petra, who is now on a postdoctoral position in South Korea. So what is the story about? Let me first start with experimental component. What happened quite recently, almost a couple of years ago, was in a sense a revolution in experimental superconductivity. What you have here is how critical temperature below which materials become superconducting increased with time. Everybody knows about corporate revolution, which happened in the middle of 80s. I remember there was low temperature conference in Japan, and at that time it was just discovered, and there was a huge interest. There was a lot of press in the conference, and I also had to talk with a journalist, and he asked me, what do you think about this discovery? I told, I hope that physics as a science will survive. And it did. But what I want to tell that surprisingly, or maybe not surprisingly, revolution that we have been watching just recently, which increased the critical temperature much more than the moving to cuprate did, was not as visible. There was not so much of enthusiasm in general public, and one of the reasons, maybe main reason, is that in order to observe this high temperature superconductivity, you need to work with extremely high pressures. But from the point of view of physics, it's still quite interesting, and I don't want to discuss how it would be applied for practical reasons, but I hope it will in this or that way. And just to give you an idea of what could be important with in terms of superconductivity applications, everything below this low line requires helium to cool. Then above this first line you can use nitrogen, and this was achievement of cuprates. Some of these materials are superconducting, can be driven superconducting using only liquid nitrogen. Now people broke another restriction, and you can cool it by this what is called dry ice, carbon dioxide, which sometimes is used for selling ice cream. And what people mean, what people really mean by room temperature superconductivity would be going beyond this last limit that will allow it to be cooled by simple water. Okay, so now I probably have to tell you what these materials are and why you need high pressure. So if you look on the content of these materials, you will see that there is a whole lot of hydrogen. So these components contain a large number of hydrogen per other atoms. And historically, it all started by this paper of Wigner and Huntington as early as 1935, who predicted that at high enough pressure, hydrogen, which we know to be a gas or maybe liquid at low temperatures, can form a solid, and they estimated, it was completely theoretical prediction, they estimated the pressure which we need to reach it as 25 gigapascal. Now people more or less agreed about something which is about 20 times higher. Just to give you an idea, in order to transform graphite into diamond, you need 15 gigapascal and large pressure. So it's really huge temperatures, and nobody up to now had reached metallic solid hydrogen, and people really tried very hard, because in 1968, Neil Ashcroft predicted that if we will manage to get this metallic hydrogen, then it will be high temperature superconductor, and temperatures would be far above room temperature, which people now estimate as 374 Kelvin. So far above room temperature. But again, the pressure needed is so huge that in spite of all attempts, and even there were a couple of publications, people claimed they reached it, but then they had to withdraw their statements. But already in this century, there appeared a new idea which revitalized whole line of research. People understood that what you can do, you can pass a good fraction of the burden of creating high pressure to chemistry, and if you will add to hydrogen some heavy ions, you can use chemical pressure and reduce the pressure needed to make this compound much below, let's say, to 150 gigapascal or so. And this is something which is not trivial, but possible to reach in the lab. Okay, so what we're dealing with, this is just how people plot the crystalline structure. We have these heavy ions, which are red balls, and these small blue balls are hydrogens, and it's believed that this type of structures can demonstrate very superconductivity at very high temperatures. Okay, now the question is how far we can go. And people who are interested in this, I just want to demonstrate one of the first papers written by Marvin Cohen and Phil Anderson about this was one of the first attempts to estimate maximum superconducting transition temperature, and they were already mentioning lattice instabilities, although they did not know a lot of what we know now, and that's why their analysis is not very adequate for today's stuff. Okay, now what's the problem? If anybody is asked what is the theory of superconductivity as phenomena, you will get the answer with 99.9% probability if you ask professional that it is Bardeen-Cooper-Schrieffer theory. It's indeed one of the most important theoretical achievements of second half of previous century, and gives a lot of understanding of what superconductivity is. But what I want to tell is that this theory is not quantitative theory in the following sense. So they invented a model which contained two parameters. One is some coupling constant lambda BCS. Another is characteristic energy scale, which is called Debye frequency in literature. And you have equations for you can demonstrate that there is appearance of so-called superconducting gap, and this gap can be within this model calculated, and transition temperature can be calculated as well, but there is no way to get the values of this characteristic energy and this coupling constant from any other experiment but measuring this delta and Tc. And the only quantitative statement of BCS theory is this relation between transition temperature and superconducting gap, which can be measured independently by, say, tunneling experiments. And this is quantitative relation, but experimentally it is qualitatively okay, but at different materials this constant 0.57 is not constant anymore. And you have other questions except what is this constant, and also this is theory of which, strictly speaking, is based on assumption that lambda BCS is small, and it's not clear how to extend it to larger coupling constants. And in order to get a large TC, you obviously need to get a large coupling constant. One thing we know from experiment is the fact that superconductivity and this BCS coupling is caused by the electron-phonon interaction, and we know it from experiments that substituted isotopes of certain atoms and observed shift of transition temperature. Okay, and again, if you look on these experiments, it's kind of inspirational, but not a proof. So we don't have on this level quantitative description. However, we still believe that we understand something about electron-phonon interaction, and there is a lot of stuff we know about phonons, about these vibrational modes in the crystal. We know thermodynamic properties such like specific heat. We know how these phonons affect the transport properties like charge transport, heat transport, and so on. And we suspect that these phonons are responsible for superconductivity. But at this point, it looks like, okay, let's now recall what we know about quantum field theory. Let's try to write down Hamiltonian of electron-phonon interaction, and from this Hamiltonian we probably will be able to somehow calculate the parameters that determine the superconducting properties. And it turns out that this approach is indeed very popular. People use several Hamiltonians, but at the same time it's rather suspicious, and I will try to explain why. Not particular form of the Hamiltonian, but the very idea that you can indeed derive everything from the particular electron effective Hamiltonian. So what are the Hamiltonians people used? The simplest one, which I will have in mind once in a while, is called Holstein Hamiltonian, but in fact the idea was first brought up by Albert Einstein, who did not write the Hamiltonian, but assumed that each iron in the lattice is an oscillator, and this oscillator is characterized by some mass and some strengths, and this oscillator is coupled with charge density, so that these oscillators and vice versa, but these oscillators are not connected with each other at all in this simple model. In principle, people use often now more advanced idea when you have indeed, in addition to electrons that are characterized by this creation and annihilation operators, you have the set of the particles called phonons, which are characterized by quasi-momentum as well, and you have interaction in the simplest form, which allows our electron to emit or absorb this phonon. And particular model which is often used in textbooks is the bimodal, where the dispersion law is linear up to certain limiting momentum, which is, of course, the momentum, the size of the brilliant zone, and above this limit, which is called the bifrequency, there is no other excitations. In fact, the situation is more complicated. If you have more complicated lattices, you, I'm sure, heard about not only acoustic but optical phonons and so on. But in general, you can all include in this Fröhlich Hamiltonian. So what's bad about this and what is suspicious? The problem is that in a sense, these phonons are more like gravitons in the theory of quantum gravity, and the reason is that what we have instead of flat vacuum in solid state is a crystalline lattice, and the curvature of the vacuum is basically deformation of this lattice. And the problem is that there is nothing like free phonon without electrons, because the lattice itself doesn't exist without electrons. And when you are seriously writing this quantum field theory and try to honestly calculate everything as we thought to do, we will find, or we can find that certain effects of interaction between ions and electrons are already included in formation of this crystalline lattice. And when you start renormalizing parameters of this Fröhlich Hamiltonian, you can take into account something that was already taken into account when you just formed the lattice. So so you cannot just take this Hamiltonian and start calculating effects like superconductivity, taken into account interaction between electrons and phonons in high and high orders. Because you have this danger of double counting, what you have to do is to use only observable phonons. So you can make other experiments like tunneling, sound, whatever you can use in order to determine the dispersion law of the phonons, but it would be real phonons where all renormalization are already taken into account. And this is what was done by people like Migdal and Eliashberg, and I'm going very quickly to first to tell what is the approach. But beforehand, if we, for example, restrict ourselves by Einstein phonons, you have frequency of these oscillators, and we understand that because of existence of these oscillators, there appears a phonon-mediated interaction between electrons, and what is extremely important that this effective interaction depends on energy transferred, so this interaction is retarded. And you can introduce effective coupling constant of this interaction, and this effective coupling constant in principle can be a candidate of something that will play the same role as coupling constant in Bardeen-Cooper-Schrieffer theory. Okay, so what we have, in principle, we have some interaction between electrons with effective dimensionless electron phonon coupling constant, and what are we doing with that? As I told, there were two papers which gave rise of this theory. One was written by Migdal at the moment where it was published, he didn't know about BCS theory, and Eliashberg 2 years later extended his this approach to describing also superconducting coupling. Okay, so I'm not going to go through all these arguments and Feynman diagrams and so on. Let me just identify the main steps that you would have if you would like to start with some electron phonon Hamiltonian. So I better write the Lagrangian, which depends on time, and what you can do in this form. So action is, of course, integral of this Lagrangian in this imaginary time. All these technicalities are not important for us. What is important is that this form is quadratic in this argument of the oscillator, and you can integrate these oscillators, these phonons, out. But since they are coupled to electrons, what you will get four fermion terms, which are, if you want, scattering of fermions by each other. And what we will get effective action that is determined, that determines this system. And at this moment, you can forget about real phonons. You have only this effective action with retarded interaction. And then what people would do nowadays, having this four fermion interaction, they will decouple it into quadratic infermions action using so-called Hubbard-Stratonovich fields, which play a role of self-energies, and then having quadratic theory in terms of fermions, you can integrate them out and have equations, have action in terms of Hubbard-Stratonovich fields. And the last step is to find the minimum this action, and at this stationary point you get the theory that can describe your system. So from original electrons and phonons, we have these effective fields and action written in terms of these fields, and the equations for stationary point are Migdal-Eliashberg equations. And this is, of course, the last step is, of course, an approximation, because we are not taking into account quantum fluctuations near this stationary point. But one can show that in the limit when Fermi energy of electrons is much bigger than all other energy scales in the problem, this is allowed to do, and stationary point equations correctly describe properties of the system. And in principle, you can try to take into account corrections which are smaller than inverse Fermi energy, but this is already another story. I'm not going to touch it. Okay. So I want to emphasize again that we don't need electron-phonon effective Hamiltonian. What we can use as a starting point is this effective action that contains only observable properties of the phonons. And the price we pay is that we now have action, so we can only calculate free energy rather than a Hamiltonian that can be used to understand better dynamics and things like that. Okay, so then just two more steps to give you an idea how it all looks, and then I will stop writing long formulas. First of all, our fields sigma and phi are time dependent, and if we are in a stationary regime, in principle they depend on two times, but in fact already on difference, and you make a Fourier transform, so they are now functions of energy, and then what you can do, you can write everything in terms of so-called Matsubara frequencies, because remember, tau is imaginary time, which changes only on from 0 to inverse temperature, and that's why your frequencies form these discrete values. And all in all, we get these equations, which you have to believe me that you can straightforwardly write using this approach that I have described. And we have this effective interaction, which depends on difference in energies. And just to remain that sigma is a real function and phi is complex function. And what you also can realize looking on this equation, that phi equals 0 is always a solution, but there could be solutions with non-zero phi, and actually phi equals 0 corresponds to normal state, and phi different from 0 corresponds to superconducting state. And the last step is just some change of variables so that I will use f and g instead of phi and sigma, rewrite these equations. And what is important for me now is that directly from these equations, you can convince yourself that there is this relation between g and f, that sum of the squares equals to 1. And this allows to kind of rewrite everything in terms of systems which we might think about in a more transparent steps, namely using this this constraint, I can tell that there will be a classical spin with square of with length 1, and components of this spin are Sz is Gn, and remember that phi, and that's why f is imaginary, is complex, so you have real and imaginary part of f which give you Sx and Sy. So for each n, remember n labels the energy, so for each energy we have a spin, and it turns out that this free energy that we wrote using this Migdal-Lashberg approach, we can think about it as a spin chain, classical spin chain, with interaction between spins that depend on the distance between them in energy space, and this dependence at large distances is 1 over squared distance. And the energy parameter is omega. It's the old frequency of this oscillator. So if our real phonons are Einstein phonon, the free energy is in fact ground state, energy of the ground state of this Hamiltonian. Okay, so we have this description, and now what do we know about it? In fact, idea of describing effect of superconductivity in terms of quasi spins is not new. And first step belongs to Anderson, who considered zero temperature problem. And actually, these Anderson spins are very widely used in nuclear physics, where this pairing effects after Belyaev and other people are described also in terms of superconductivity. So basically, you start with one particle picture of finite system, and you have certain set of orbitals which are labeled by this parameter alpha, and each orbital allows, in principle, two fermions with spin with opposite spins, and each of them will have energy that depends on this orbital. And when you populate this system with fermions, you can have one particle either spin up or spin down on an orbital, and these orbitals are called blocked orbitals. And unblocked are either double occupied or empty. If let's say they're double occupied, we will tell that we have instead spin 1/2, and if it is empty, it will be spin minus 1/2, so not real spin, but quasi-spin. And this is quite important for analyzing BCS interaction, because BCS interaction in these terms is basically interaction that allows a pair of fermions with opposite spin that occupy one orbital to get to another orbital. So basically, in terms of this pseudospin, it is XY interaction. We apply sigma plus for orbital alpha and sigma minus for orbital beta. So instead of having spin up here, spin down here, we have opposite. And this is BCS interaction, and the BCS Hamiltonian in terms of pseudospin can be written in this form. You have one particle energy which looks like effective magnetic field in z direction, which depends on the energy of the orbital, and you have effective XY interaction of this spins. And this form that we found is more or less similar, except that our spins are classical non-spins 1/2. And interaction that in BCS model was every spin interacts with every other spin. Now it has some dependence on the distance, but those spins which are close to each other, or when the two energies are close to each other, we indeed have distance independent interaction. And in this picture, the difference between normal and superconducting state is that normal state has this domain structure. All states with energies below what is called Fermi energy are occupied. All states above are empty, and we have very sharp domain wall. But as soon, so if electrons don't interact with each other, this is exactly what we have. But when we introduce the XY interaction between these two spins, between pairs of spin, existence of this domain wall becomes costly, and at certain energy, this domain wall gets softening. Instead of having sharp transition, we have this transition smeared over a certain energy interval. So there appear certain energies which are not totally occupied or not totally empty, but rather they are partially occupied, and transition between these two types of the distribution is superconducting transition. Okay, this is just to give you an idea of what we have in order to describe physics of this metal. And now I just want very quickly to emphasize what we have for strong electron, for strong coupling. And in fact, for strong coupling, we have more or less universal limit when effective lambda goes to infinity. We don't care what are the frequencies of the real phonons. Effective interaction is just inverse distance. And what people learned long ago is that instead of this BCS formula, which contains a coupling constant in the exponent, we have another formula so that Tc is proportional to omega and also square root of lambda. So if we can fix omega and increase lambda, it looks like Tc is unbound. And this was for a long time kind of common understanding that in principle there is no limits in the in this Eli-Ashberg theory that limit transition temperature. Okay, now what I want to tell that it's not completely correct. So lambda cannot be arbitrarily big, and that's why Tc also cannot be arbitrarily big. And the reason is the following. Let's forget about superconductivity and think only about normal properties, which we know very well because we have free energy and we know distribution of the spins, which is this domain wall. So we can calculate specific heat, and this is the result of the specific heat. There is prefactor, which is determined by electronic density of states, and we have certain function of the ratio between the characteristic frequency omega and temperature, and this function is just particular function described by logarithmic derivatives of the gamma function. So something, this is explicit form for the specific heat, and it's known since 60s. I think Prange and Kadanoff were the first to write something like that, but for sure Lee and Reiner derive it very rigorous way. Okay, so what's bad about this? We have this specific heat, and if we will start plotting this specific heat as a function of temperature, we will find that when lambda is small, this is kind of okay. We have certain temperature dependent specific heat, but it's still does not show any problems. But what happens is that we start to have some dynamics when we go to stronger lambdas, and when we go through certain threshold, specific heat appears to be negative at certain temperature interval. And this is actually the problem, because negative specific heat means instability of the whole system. We don't know what is stable state, but we know that the state we started with is not stable. Now, in principle, if we would have Hamiltonian description of whole system, it's simply impossible, because by construction, for any system that is described by particular Hamiltonian, a specific heat can be proven in an easy way to be positive. But our interaction between these effective spins contains temperature not in a usual way, but also as a parameter of this effective Hamiltonian, and that's why this problem appears. Now, what can we do, and what all this means? In fact, some people would tell you that it's not as dangerous because, okay, it's only a specific heat of electrons, but there are real phonons which are flying there, and specific heat of phonons is positive, and that's why total specific heat is positive, and no reason to worry about that. But it turns out to be not correct. And the reason is that in principle, if you will start to think in terms of stability, you will find what you can do. Let's say if you take your electrons out of equilibrium with phonons, normally it will with time go to this equilibrium, and you can write Boltzmann equation that will describe this process. And indeed, your collision integral contains this combination which vanishes in the equilibrium when both capital N distribution of phonons and small n distribution of electrons have the same temperature. But it turns out that at the point where specific heat of electrons changes sign, also the collision integral has pathological sign. So instead of suppressing the difference between distribution of electrons and equilibrium distribution, it starts to increase it. So it always happens when instead of effective minimum, we have actually maximum. So if our system is in a highly excited state. And this is what we mean. So it means that equilibrium at temperature T, which we think takes place, is not stable, and system still is not stable. So we have to understand what is going on and whether there is some kind of dealing with this problem. So in the simple case of Einstein phonons, as I told, we have particular coupling constant where at least Migdal-Eliashberg theory breaks down. If you want, it's still a stationary point of all the consideration, but it's not longer a minimum. And now the question is how far in reality we are from this point. In fact, for conventional superconductors, you can see that all of effective lambdas are much smaller. The biggest are some combinations based on lead and bismuth, but they're still 3 or smaller. And indeed, what you can see is that there is almost nothing with lambda above this critical limit. And what you see in this picture are materials with particular value of lambda, and closed circles or triangles are materials that already exist in the lab, and open means that they are only on paper and predicted, and as far as I understand, this material with lambda about 4 plus was never observed yet. So in principle, this criterion is satisfied, but we have to go further. And at this point, we were approached by the experimentalists, because we were not thinking about hybrids, we were thinking about applicability of Migdal-Eliashberg theory. And now let's see what we have for in more general case. For example, for phonons with some dispersion and so on. There is so-called Eliashberg function, which known to be determining all the properties of the system if it is described in the framework of the theory. And this function is a result of this summation. And now what is important, that omega q and gq are not some unknown and God knows what the bare phonons. It's observable phonons which we can understand or measure in other experiments. And there are ways, I'm not going to go into details, there are ways to measure this Eliashberg function directly. And it turns out that it is a pretty complicated function in reality. And on the left, we have this yttrium H9 at 200 GPa. People, I don't even know whether it is measured or calculated from the first principles, but this is what we were given. And just if you compare it with old known Eliashberg functions for conventional materials like zinc, what we have more or less the same shape, but if you will compare the energy scale, you will find that it is about, energies here are about 20 times larger, because of course hydrogen is light and corresponding oscillator frequencies should be large. Okay. Now all these parameters. Now I'm going from Einstein phonons to expressing everything in terms of the Eliashberg function. And what we can write is the stability condition that this quantity psi, which is determined by this convolution of the Eliashberg function with this one based on all these de Gamma functions, should be smaller than 1. So indeed, this is sufficient, but not necessarily. This is necessary, but not necessarily sufficient condition. So it can be, system can blow up at when this is still satisfied, but it looks like psi never can be bigger than 1. Now I'm almost at the end, and I just want to demonstrate what we learned from the experiment of these materials based on hydrogen with additional heavy ions. So what happens, actually, when I first heard about the metallic hydrogen and all this stuff, I thought that the main problem is pressure, and the bigger the pressure, the higher TC. We just don't have means to apply strong enough pressure. In fact, situation is opposite. if you go to very high pressures, Tc is relatively low, and with reduction of pressure, it increases. It's almost always increases. And at the point where it reaches maximum, the system becomes unstable. So this instability actually takes place in these materials. What is instability? It's not very well known. Let me see. Yeah, but what we can see is how the Eliashberg function evolves when you change the pressure. So if pressure is high, you have even somewhat bigger energies. But what gets developed is this huge peak at certain frequency, which probably is responsible for high temperatures, superconductivity, but also is responsible for instability. This is for lanthanum and deuterium compound. If you want to ask me about isotope effect and substitute deuterium by hydrogen, we have more or less the same story here, that there is this peak which gets developed and finally leads to the instability. And as I told, instability doesn't mean that system undergoes some simple structure, some simple restructuring. What they observe is that system loses hydrogen, and your lattice gets destroyed, and basically the system blows up. And if you ask me how is our criterion, it turns out that at the point of instability, this psi, which for sure should be smaller than 1, it gets substantially smaller than 1, more like smaller than 1/2, and then system becomes unstable. But as I told, our statement is that psi should be bigger than 1, and not that everything is always stable when psi is bigger than 1. Okay, so this is a lot of information of all these experiments, but there is also some idea that might, do I have another couple of minutes? So, yeah, that might be interesting. In fact, when you reduce the pressure, you are still in a metallic state. And what happens when you go into superconducting state, you may develop you are developing a gap, and if, for example, you change crystalline structure and instead of metal get insulator, you also develop a gap in the energy spectrum, and both gaps allow you to reduce the energy. So, in principle, you can think about system wants to change the symmetry of the lattice, and create gap in the spectrum, but it can have a choice between insulating and superconducting gap. And idea is the following, that suppose we will not start with metallic state and cool it at given pressure. Then we can reach this instability. Suppose we will first cool it and then to superconducting state and then reduce the pressure. Can we get beyond this limit in a quasi-stable superconductivity? And idea is the following, that this is very schematic way of what I told you. This is pressure, this is transition temperature. So this red line, which is observed, and then what people know is that it is this black line that corresponds to developing of this instability, losing hydrogen, and God knows what. But what if we first cool system, then reduce the pressure already at low temperature, and then start heating it? Will superconductivity disappear? Will this low temperature material be stable or not? I don't know, but there is a chance that because we're in a superconducting state, our specific heat is different, electron contribution is suppressed, and this system can be still quasi-stable. And something like this was observed. This is my last view graph, that in a completely different system called iron and selenium, which has superconductive transition temperature about 10 Kelvin at ambient pressure. But at higher pressures, it has much higher transition temperature. It turns out that if you will first apply the pressure and then cool your system in a superconducting state, this superconducting state will survive much above what it is at temperatures that are much above the temperatures where it will be destroyed. Sorry, I'm not taking questions. Yeah. So in principle, this phenomena of metastable superconductivity exist, and the point is that it might really allow us to go even above the limit that I explained, and will boost our limits of superconductivity towards real room temperature. But the last word, of course, belongs to experimentalists. Okay, I'm sorry for a long story. Thank you very much, and I would love to answer any questions.
Thanks for the nice talk. Questions?
Thanks for the nice talk. How does the pressure enter into this Eliasberg theory? Can you sort of, is that a phenomenological way to adjust coupling constants? But because the formulas don't contain pressure, right? So
no, well, formula doesn't contain pressure, but formula contains parameters of the phonons, like their frequencies. And clearly, if you change the pressure, your effective phonon spectrum changes.
Okay.
This is how they.
But that's known how this pressure dependence
So
or you make some assumptions?
First of all, in principle, you can measure real phonon, but you need whole spectrum. There are all these methods, Raman scattering, whatever, but I'm not sure that they made these measurements for these materials. So you also can do something like first principle calculation. So you don't start with particular lattice, but just get ions and phonon electrons and do calculations. I don't think they did that. So I think what they did was assuming certain lattice, which they might have calculated and maybe even measured by some X-ray, and then by calculating properties of the phonons, they can end up with a Eliashberg function. So there are papers, but they are so much involved in numerics that I cannot guarantee just what we were given.
Thank you.
Fascinating talk, really.
Yeah.
Experimentally, and also from the point of view of your theory, wouldn't one expect that there are other competing instabilities like charge density waves that take place before specific heat becomes negative?
There could be. There could be. I think what is here is what I discussed is effect of retardation. So in principle, what you are speaking about are properties of the Fermi liquid. And we know that in Fermi liquid, indeed, there are two types of instabilities and nothing else. But what we have here, it's only, phonons are in the name, but not in the heart of this approach. What is in the heart is still properties of electrons which interact with each other by interaction that is retarded. And it looks like this retardation brings a new twist to the Fermi liquid, or new instabilities. But of course, there can be, in addition to that, there can be instabilities that you are speaking about, because nobody abandoned direct interaction between electrons and things like that. But it turns out that, in a sense, there is this, people refer to Macmillan's paper, that when you have both this retarded interaction and normal interaction, there is certain suppression of the direct column interaction by this. So what would be stability in the presence of both direct interaction and retarded, I don't know. But what I want to tell is that retarded Fermi liquid with retarded interaction is something could be something qualitatively different.
More questions?
But are you sure they are still Fermi liquids, these metallic phases?
Well, it's a matter of definition. No, you see, what is Fermi liquid in nowadays, people like so much to speak about non-Fermi liquid things that, you see, I think a lot of people are mad on me because I used to repeat the difference between Fermi liquid and non-Fermi liquid is the same as difference between bananas and non-bananas. Yeah, but the question is what you call non-Fermi liquid, and clearly, if you will study things like lifetime of this fermionic excitation, you will have problems simply because here we are speaking about large high temperatures, and lifetime is already not as large, but it's indeed dominated by electron-phonon interaction rather than by collision between electrons. Now, I can tell you that there is a kind of distant relative of the problem, let's say, of Einstein phonons, and the problem that people in strongly correlated system know very well, namely two-channel Kondo effect. Because if instead of these oscillators, you have just two-level system on some sides, and the splitting is smaller but zero, this interaction still brings up certain effective interaction between electrons. But then we know that even in the limit when capital omega tends to zero, then we still have non-Fermi liquid behavior. So in this sense, it could be non-Fermi liquid. But what we usually think about when speak about Fermi liquid, non-Fermi liquid, are very low temperature properties. At high temperatures, God knows. Yeah.
More questions? Well, if not, let's thank Boris again.
Thank you.